Today's discussion centers on the research paper L3DG, Latent 3D Gaussian Diffusion, which introduces a novel approach to generative 3D modeling. The authors propose using a 3D Gaussian primitives and a latent diffusion model for efficient and high-fidelity 3D scene synthesis, even scaling to room-sized environments. Let's start with the core innovation. What problem does L3DG solve, and how does it differ from existing methods?
L3DG addresses the limitations of existing generative 3D models in handling the complexity and scale of room-sized scenes. Many methods struggle with either the rendering efficiency or the scalability of generating highly detailed, large-scale 3D content. L3DG leverages 3D Gaussian splatting for efficient rendering. But the key innovation lies in its use of a latent diffusion model operating on a compressed latent space of these Gaussians. This compressed representation, learned via a VQ-VAE with sparse convolutions, allows the model to handle the vast number of Gaussians needed for large scenes while maintaining high detail at the object level. This contrasts with methods that operate directly on high-dimensional 3D representations, which are computationally expensive for large scenes.
The use of a VQ-VAE with sparse convolutions is crucial for scalability. Can you elaborate on the architecture and its role in compressing the 3D Gaussian representation?
The VQ-VAE acts as a powerful encoder-decoder pair. The encoder, built with a sparse convolutional architecture using Minkowski engine, efficiently processes the sparse, grid-assigned 3D Gaussians. Sparsity is key here because it avoids processing empty space. The encoder maps the sparse Gaussians to a lower-dimensional, dense latent grid. Vector quantization then discretizes this latent space, allowing for efficient storage and manipulation. The decoder, using generative sparse transpose convolutions, reconstructs the 3D Gaussians from the quantized latent representation. This entire process significantly reduces the dimensionality of the data fed into the diffusion model, enabling scalability to large scenes.
The paper mentions a generative sparse transpose convolution. How does this differ from a standard sparse transpose convolution, and why is it necessary?
Standard sparse transpose convolutions rely on cached coordinates from the encoder during upsampling. The generative variant, however, generates new coordinates in each upsampling layer. This is crucial because the decoder needs to operate independently at test time, synthesizing novel scenes without access to the encoder's cached coordinates. A pruning strategy is then employed to control the number of active voxels, preventing an explosion in computational cost.
Let's delve into the latent diffusion model itself. How does it work in conjunction with the compressed representation, and what are the advantages of this approach?
The latent diffusion model operates on the low-resolution, dense latent grid produced by the VQ-VAE. This is a crucial step because the diffusion process needs a dense grid to generate content anywhere in the scene. The model learns to denoise a sequence of increasingly noisy, latent representations, starting from pure noise and iteratively refining the details until a clean sample is obtained. This denoising process happens efficiently in the low-dimensional latent space, significantly reducing computational cost compared to operating directly on the high-dimensional 3D Gaussian representation. The occupancy channel is also used to sparsify the generated latent grid before decoding back to the 3D Gaussian representation.
The paper highlights significant improvements in FID and KID scores compared to baselines like Diff-RF. Can you comment on the qualitative differences observed in the generated outputs?
The quantitative improvements in FID and KID reflect a substantial increase in the visual fidelity of the generated 3D models. Qualitatively, L3DG produces sharper, more detailed results, particularly in areas with fine structures like chair legs or table details. Compared to Diff-RF, which uses radiance fields, L3DG exhibits fewer artifacts and better handles thin structures due to the higher resolution and flexibility of the Gaussian representation. Kazgan-based methods, while faster in generation, often suffer from view-dependent inconsistencies and artifacts that L3DG avoids.
The paper demonstrates scalability to room-sized scenes. What are the key challenges in achieving this scalability, and what are the limitations of the current approach?
The key to scalability lies in the efficient latent representation learned by the VQ-VAE and the ability of the diffusion model to operate effectively in this compressed space. However, limitations remain. Larger neural networks would likely improve the quality and extent of generated scenes, but this requires more computational resources. Furthermore, the current approach relies on synthetic datasets. Applying L3DG to real-world datasets with high-fidelity 3D ground truth remains a significant challenge due to the limited availability of such data. Additional training strategies, such as spatial subdivision, could also improve efficiency and scalability.
The paper mentions the use of spherical harmonics for modeling view dependence. What is the role of spherical harmonics in this context, and how does it contribute to the realism of the rendered images?
Spherical harmonics are used to represent the view-dependent color of each 3D Gaussian primitive. Instead of storing a separate color for each viewing direction, spherical harmonics provide a compact representation that allows for efficient rendering from arbitrary viewpoints. This is crucial for generating realistic images because it captures the subtle variations in color and lighting that occur as the viewpoint changes. The degree of spherical harmonics used, degree 1 in this case, represents a trade-off between accuracy and computational cost.
The ablation study reveals the importance of both the RGB loss and the perceptual loss in training the VQ-VAE. Can you explain the role of each loss function and their impact on the final results?
The RGB loss directly minimizes the difference between the rendered colors of the reconstructed 3D Gaussians and the target images. This ensures that the generated models accurately reproduce the colors and textures of the training data. The perceptual loss, on the other hand, uses a pre-trained VGG network to compare features at different levels of detail, encouraging similarity between the reconstructed and target images in terms of higher-level visual features. The combination of these two losses is crucial for achieving high-fidelity results. Removing either loss leads to a noticeable decrease in visual quality, with the absence of perceptual loss resulting in a more significant drop in sharpness and detail.
The paper uses an L1 color loss and SSIM for optimizing the 3D Gaussian primitives during the initial reconstruction stage. Why is this combination of loss functions chosen, and what are the advantages of using SSIM?
The L1 color loss measures the absolute difference between rendered and target pixel colors, providing a simple and effective way to minimize color discrepancies. SSIM, on the other hand, considers the structural similarity between images, capturing higher-level perceptual aspects beyond simple pixel-wise differences. The combination of L1 and SSIM ensures that the reconstructed 3D Gaussians accurately represent both the color and the structural details of the scene. SSIM is particularly advantageous because it is more perceptually aligned with human judgment of image quality than simple pixel-wise error metrics.
The training process involves several stages: optimizing the 3D Gaussians, training the VQ-VAE, and training the diffusion model. Can you describe the overall training pipeline and the dependencies between these stages?
The training pipeline is sequential. First, the 3D Gaussian primitives are optimized for each scene using multi-view images and the combined L1 and SSIM loss. This stage produces a set of optimized 3D Gaussians that accurately represent the scene geometry and appearance. These optimized Gaussians are then used to train the VQ-VAE, which learns a compressed latent representation. Finally, the latent diffusion model is trained using the latent representations generated by the VQ-VAE. The VQ-VAE acts as a bridge between the high-dimensional 3D Gaussian representation and the low-dimensional latent space where the diffusion model operates.
The paper mentions a densification strategy during the 3D Gaussian optimization. Can you explain how this strategy works and its purpose?
The densification strategy dynamically adds new Gaussian primitives to regions of the scene where needed. It monitors the positional gradients of existing primitives in view space. If the average gradient magnitude exceeds a threshold, indicating a need for higher resolution, a new primitive is created in the corresponding voxel. This new primitive is initialized with parameters derived from its neighbors, ensuring a smooth transition. This adaptive densification allows the model to efficiently represent both fine details and large-scale structures without requiring a fixed, high-resolution grid from the start.
The choice of hyperparameters, such as the voxel size, densification and pruning thresholds, and loss weights, seems crucial. How are these hyperparameters determined, and how sensitive are the results to changes in these parameters?
The hyperparameters were determined through experimentation and validation on the training datasets. The voxel size, for instance, determines the initial resolution of the sparse grid. The densification and pruning thresholds control the dynamic adjustment of the number of Gaussians during optimization. The loss weights balance the contributions of different loss terms during training. The paper doesn't provide an exhaustive sensitivity analysis, but the ablation study demonstrates the importance of each component and the impact of removing certain loss terms. Optimal hyperparameter settings are likely dataset dependent and may require tuning for different applications.
Finally, what are the potential future directions for this research? What are some of the limitations that could be addressed in future work?
Several avenues for future research exist. Scaling to even larger scenes and higher visual fidelity could be achieved by using larger neural networks and exploring more efficient training strategies. Extending the approach to handle dynamic scenes and incorporating more complex material properties would also be valuable. Furthermore, applying L3DG to real-world datasets with high-fidelity 3D ground truth would significantly enhance its robustness and generalizability. Investigating alternative latent space representations and diffusion model architectures could also lead to further improvements. Addressing the computational cost associated with the initial 3D Gaussian optimization is another important area for future work.
The authors mentioned that their implementation is unoptimized. What are some potential avenues for optimization, and how could these optimizations impact the training time and rendering speed?
Significant optimizations are possible. Parallel processing of the 3D Gaussian optimization could drastically reduce the training time. More efficient implementations of sparse convolutions and the diffusion model could also improve speed. Furthermore, exploring alternative hardware architectures, such as specialized hardware for sparse computations, could further accelerate the process. These optimizations would not only reduce training time, but also improve the rendering speed, making the generated models more suitable for real-time applications.
The paper compares L3DG against GAN-based and diffusion-based baselines. What are the key advantages and disadvantages of each approach, and why is L3DG a compelling alternative?
LDAM-based methods are often faster in generation, but can suffer from training instability and mode collapse. They may also struggle to generate high-fidelity details and consistent views. Diffusion-based methods, while capable of generating high-quality results, can be computationally expensive, especially for high-resolution 3D models. L3DG combines the advantages of both approaches. It leverages the efficiency of Gaussian splatting for rendering and the high-fidelity generation capabilities of diffusion models, while the latent space compression significantly reduces the computational cost, making it a compelling alternative for generating large-scale, high-fidelity 3D scenes.
The use of a sparse grid for representing the 3D Gaussians is a key aspect of the method's efficiency. Can you discuss the trade-offs involved in choosing the sparsity level and the impact on both the accuracy and the computational cost?
The sparsity level represents a trade-off between accuracy and computational cost. A denser grid allows for more precise representation of the scene, but increases the computational burden. A sparser grid reduces computational cost, but may sacrifice some detail. The adaptive densification strategy employed in L3DG helps to mitigate this trade-off by dynamically adjusting the sparsity level based on the scene's complexity. The choice of voxel size and the densification/pruning thresholds are crucial parameters that influence this balance. Finding the optimal sparsity level often involves experimentation and depends on the specific application and the desired level of detail.
The paper shows results on 3 datasets: photo-shaped chairs, ABO tables, and 3D front rooms. How are these datasets chosen, and what are the characteristics of each dataset that make them suitable for evaluating L3DG?
The datasets were chosen to represent different scales and complexities of 3D scenes. Photo-shaped chairs and ABO tables provide benchmark datasets for object-level generation, allowing for quantitative comparison with existing methods. 3D front rooms, on the other hand, offer a challenging dataset for evaluating the scalability of the method to room-sized environments. The characteristics of each dataset, such as the number of views, image resolution, and the complexity of the object scenes, are relevant for assessing the performance of L3DG in terms of both visual fidelity and computational efficiency.
The paper uses the chamfer distance to compute geometric nearest neighbors in the training set. Why is the chamfer distance chosen for this purpose, and what insights does this analysis provide?
The chamfer distance is a common metric for comparing point clouds, making it suitable for measuring the geometric similarity between the generated 3D models and their nearest neighbors in the training set. By computing the chamfer distance between the point clouds sampled from the generated 3D Gaussians and the point clouds from the training data, the authors can assess whether the model is simply memorizing the training examples or generating truly novel shapes. The results show that the generated chairs are substantially different from their nearest neighbors, indicating that the model is capable of generating novel samples rather than simply retrieving from the training set.
The paper concludes by highlighting the potential of L3DG for various applications in computer graphics. Can you elaborate on some of these potential applications and the broader impact of this research?
L3DG's ability to generate high-fidelity, room-sized 3D scenes opens up exciting possibilities in various applications. It could be used for creating realistic virtual environments for gaming, virtual reality, and augmented reality experiences. It could also be applied to asset creation for films and animations, architectural visualization, and robotics. The efficient rendering capabilities of Gaussian splatting make L3DG particularly suitable for real-time applications. The research contributes to the broader field of generative 3D modeling by providing a scalable and efficient method for generating high-quality 3D content, paving the way for more realistic and immersive experiences in various domains.
This has been a thorough discussion of the L3DG paper. Thank you.